All right, Formula fans, welcome back to the Engineer's Corner questions and the breakdown of them. Let's dive right into this one. So we have a wing configuration, we have its Z mode and X mode. So Z mode being high drag, X mode being the low drag, or the infamous DRS configuration. So when you see these F1 cars going around the track, this is essentially kind of a breakdown or a calculation that you can do to kind of understand how much power is being freed up. And that's basically what the question is asking. How much power is being freed up when this wing does this? And the answer was 206 kilowatts, or approximately 276 horsepower. And if you want to know the why, let's get into it. Let's talk about why and how this actually happens. All right. So the finer details, it's not two wings, it's two wing configurations, one car. We have Z mode, which is the high drag mode. Our coefficient of drag sits at 1.05. This is a given value. We assume the aerodynamic engineers have optimized their wings, have done their analysis, their wind tunnel testing, and they're like, hey, this is the coefficient of drag for you to factor in as you're considering all the turns and the straights and the wing configuration. And then we have X mode, which is a low drag mode, which the CD, or the coefficient of drag, is 0.65. Now notice it's dropped down, right? So we're assuming the wing is a little bit more optimized or streamlined, which makes sense because when they go into the DRS mode, the wing flattens, right? We have less camber, it's less curved upward, so less downforce, and they're able to pick up a bit more speed. So let's decompose down into the drag force. So what is it? So drag force is simply 1/2 times the density of the air, or rho, times the coefficient of drag, or CD, times A, which is the frontal area, times V squared, or the velocity, which is in meters per second. And this is the drag force that we are asking the engine to overcome. Now pay close attention to CD, or the coefficient of drag. We indicated that there are two modes within this car. There are Z mode and X mode, or high drag and low drag mode. And that influences this drag force, which then influences the power output that we're asking the engine to produce to overcome this drag force, right? So logical process here. Let's think about it and step through it. So what is the cost of power, right? So in this case of the power equation, we have it as P equals D times V, or drag times velocity. So we're saying that in order to overcome this drag force at this velocity, you need to produce this much power. So that's kind of the root of the equation. Now remember, we have the drag equation, we have D. So let's plug D into this power equation and actually decompose it down and further refine this equation and get to the root of it. So when we do that, we end up with 1/2 rho, which is the density of the air, times CD, which is the coefficient of drag, times A, which is the frontal area, times V cubed, right? So V to the third power, because there's that additional V in the power equation. So this is how we describe how much power we're asking the engine to produce or require in order to overcome this force that's working against this car at this speed. And it's expensive. It's pretty expensive, folks. V cubed, that's nasty, right? Because, we're talking 300 kilometers per hour. So when you enter the cubed realm, it's V times V times V rather than just V times V. So, mathematically, that's quite a jump, right? So not a cheap item to overcome. So you can begin to imagine how significant the DRS mode, or these low drag modes on these cars, play, how significant a role they actually play, which is fantastic, right? It's pretty awesome to see. So we plug in the details of the car. These were given in the question. We discuss the speed. We have the air density. I give that. We give the frontal area. And then we have our coefficient of drag, which is Z mode and X mode. And we go into the details. So we first assess the power equation, which had that V cubed value for the high drag mode, which we see CD at 1.05 in the middle of the equation. And we are essentially saying that the amount of power required to overcome this drag is 541 kilowatts, which is approximately 725 horsepower at the wheels just to part the air, which is pretty significant, right? That's quite a bit. And then we go to this stalled wing, or this flattened wing, or this more optimized wing for the straights, and we change that CD or the coefficient of drag right in the middle, which is 0.65, and we end up with a power to overcome that level of drag is 335 kilowatts, or approximately 449 horsepower. So that's a huge change, right? And we'll look at that delta now. So when we assess how much power is freed up, we're essentially looking at the difference, like how much power is actually freed up, and that's 206 kilowatts. So that's quite a bit, right? That's quite a bit of power, and let's describe what that looks like. So it's approximately 276 horsepower from a geometry shift. So when you guys are watching these races, and you see that wing drop, and I know there's other cars right next to them, so they look like they're racing toe to toe, but there's a lot of power being freed up for this car to use, right? So that's not a minor shift. So and to give you an idea here, the drag power freed up by X mode in 206 kilowatts, that's approximately 52% of the internal combustion engine. That's quite a bit. It emphasizes why it's such a centerpiece, right? Why it's such a major item to consider in this sport, and why aerodynamics is so important, right? Because you you see these guys just drop a wing down, and you're like, oh, okay, cool, they're gonna go fast now. But it's like, what does that actually mean? This is what it actually means, and I think it's beautiful. It's really a beautiful thing to see and understand. So in a nutshell, right, the drag power scales with V cubed, which is significant in terms of cost. The wing optimization is a major factor. When we drop that wing, we are essentially optimizing the wing configuration for the operation for that straight, and that plays a huge factor. So hopefully this was an eye-opener for folks that don't know this stuff, that haven't come across these equations. Hopefully this is helpful for the students that are in the midst of trying to interpret and understand these questions, and understands, like, how do I take these equations and apply them to the real world? And hopefully this was just fun all around. And thank you guys for engaging. And if you have any questions, please, by all means, comment down below, and we'll continue the conversation in the chat there. So I hope you all are doing well, and I hope you guys are enjoying the season. And let's see what's in store for us coming up here next. All right, take care.